All right, picking up where I was going to start off in lecture or lab, but decided not to. Intermolecular forces. This is what keeps us together. Not us as like the class, but our individual bodies. Keeps them all in one piece mostly. It's the intermolecular forces. This is like little sticky forces that hold everything together. So it keeps the solids and the liquids in touchingly close proximity. It's from interactions between charges, like in ions, particle charges, like in polar molecules and things that can do hydrogen bonding, and temporary charges, like with little fluctuations in the electron field. Coulomb's law comes into effect sort of here. We're not going to really do any calculations with Coulomb's law, but the idea is that we've got two charges up top, charge 1, charge 2. Charge 1 and charge 2 get bigger, then that will also increase the size of our potential energy, or that attractive force. And if we decrease the distance between our two charged particles, that also increases the attractive force. Bonding forces involve large charges, so like our hydrogen and our oxygen in water are large charges at close distances. Our intermolecular forces are much smaller charges. This is much less than 1 charge unit, where like a proton has +1, an electron has -1. It's much less than 1, and it's a much further distance than with our bond. So that's what makes it, some of the things that make it a lot weaker. The first force, the one that everything has, which is not entirely true, but most things have this, is called the dispersion force. And this is the result of fluctuations in the electron distribution. So we've talked a little bit about effective nuclear charge. This is sort of related to that. It's a similar idea. Within a given atom, at any moment, we've got 3 frames shown here. At any moment, the electrons can be anywhere within our expected distribution, which is represented by the blue bubble here, like a big s orbital. So we've got in frame 1, they're roughly evenly distributed, one on the bottom, one on the top. They're slightly different spacing. And then in the very next instance of time, they've moved. They've possibly swapped places, they've possibly just rotated, but they're still on opposite sides. And then suddenly, for no explicable reason, in frame 3, both of them are on what we see as the left side, and there's nothing shielding the nucleus on the right side. And because there's nothing shielding the nucleus on the right side, we get a partial positive charge, and we've got 2 electrons on the left side, so that's going to be a little bit more negative because they're a little further away from the nucleus, and since they're together. And then if we continued this sequence, in frame 4, that might be gone. Frame 5, it might still be gone. Then it might come back for frame 6 and 7 and 8, and then it might disappear again. So this is like before you could register that it's even there, it would be gone already. And then it might have come back and gone away another 100 times. But it's these moments, like in frame 3, that cause the dispersion force, or that are the reason that they're a little bit sticky. But because it's around for such a short amount of time, we call it an instantaneous dipole. And that also makes it really, really weak, because it's not even there all the time. And here's what it might look like between a bunch of helium atoms. So let's say this first one on the left, this atom, both the electrons the left side. And then it just happened to be very close to a neighboring helium atom. That positive charge then induces or pulls over the electrons. And that can set off a chain reaction. If there's another one that's very, very close, that could draw in the electrons of a neighboring helium atom. And then you blink and it's gone. They've all separated again. If it's very, 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 very cold, like 4 Kelvin cold, then this is enough of a force that the helium atoms will actually stay together, touchingly close as a liquid. And if I understand correctly, helium basically doesn't exist as a solid. So a couple of things that affect the strength of the dispersion forces. Since the dispersion force is based on how easily the electrons can move, how easily they could be pulled over to one side, or how many could be pulled over to one side, we've got a couple of things that affect it. A larger electron cloud can affect the strength of our dispersion force. So having more electrons, and also having the electrons further away from the nucleus. Because of that reduced effective nuclear charge and distance. And so dispersion force generally increases with molar mass. This applies within a family of chemicals. So a family is another term that we might use for a group on the periodic table, a column. So what we're looking at in table 12.3 here is all of our noble gases arranged in the order that we see them on the periodic table. And we've got the molar mass and the boiling point just to show you how boiling point increases with molar mass. So with helium, like I was saying, it was about 4 Kelvin. And a molar mass of 4, if you increase the molar mass, the boiling point goes up. If you increase it again, the boiling point continues to go up until we get up to xenon with a boiling point of 165 Kelvin. So only about negative 110 Celsius. So that would be one example of a type of family. Another time that we can use this trend of molar mass is if we're comparing similar types of compounds, so hydrocarbons, methane, ethane, propane, butane, etc. Things that are just hydrogen and carbon. So like hydrocarbons. Just hydrogen and carbon. Those will also have similar chemical properties, and as we add more carbons and hydrogens, they get bigger, and so the boiling point also goes up. The shape also plays a role. So comparing a couple of types of hydrocarbon, we have N-pentane. N just means normal or straight chain. So it doesn't branch off at any point. And then neopentane, just a prefix referring to this particular shape of pentane. Both of them have 5 carbons and 12 hydrogens. So they've got the same molar mass, but they have different boiling points because of their different shapes. Dispersion forces is sort of like the friction of molecules and atoms, at least when we're talking about nonpolar things. That's how nonpolars stick together. So for N-pentane, they exist as these little spaghetti noodles. For neopentane, we've got the 1 carbon in the middle and then 4 on the outside, and so they're kind of spheres, or approximately spherical, whereas our our N-pentane is long and skinny, and so it's going to have more space, more surface area basically that it can interact with nearby molecules. And that larger area means that it will have stronger forces, and the stronger forces means that it takes more energy to separate. For a lot of this, I think we're going to see boiling point used as our proxy for intermolecular forces strength. So a higher boiling point means stronger intermolecular forces. And this is what dispersion forces look like for all of our straight chains from 5 carbons up to 9 carbons. As we increase the molar mass, the boiling point also increases. And this is in degrees Celsius. So hexane is a common solvent used in the lab. Octane is one of the main ingredients in gasoline. If we went shorter than N-pentane, this is like maybe 35-ish degrees Celsius. So that would boil around here during the summer. If we went shorter to butane, that is also going to boil in most conditions. And if you go shorter to propane, propane is what we use to grill on the outdoor grills. Ethane we don't really use, and methane is what we use in our houses if you have a gas grill. So we don't use those in our gasoline because they would just evaporate. Octane's a nice middle ground. Okay, trying to apply those same ideas, which of these halogens would we expect to have the highest boiling point? U2 what?
C.
Yes, it's iodine. Why is it iodine?
It has the biggest molar mass.
Yeah, largest molar mass. Largest molar mass, strongest intermolecular forces because it's got the most electrons to just randomly happen to have on one side of the molecule or the other. Also, we can kind of cheat with the periodic table that we have in our class because it shows you the state of matter at room temperature, I think. So chlorine is a gas, bromine's a liquid, iodine is a solid, allegedly. So that's our first force. And again, everything has dispersion forces. The little caveat being that you need electrons. It's like if we have a proton, it's not going to have dispersion forces because it doesn't have any electrons. It's just a proton, it's just an H+. All right, our next force, and our slightly stronger force, is the dipole-dipole force, a force between two dipoles. That's why it's dipole-dipole. So the dipole-dipole exists in all molecules that are polar. The reason that this exists is because polar molecules have a permanent dipole. It is stronger than dispersion forces. the way that my brain thinks of it is it's always around. I don't know what the actual magnitude of the charges is. I'm sure there's numbers out there. But it's always around, and so over time, you're going to average out to having stronger forces, even if they're the same magnitude of charge. So if we look at whatever these molecules are, these have a dipole, a separation of charge between the oxygen, which is more electronegative than the carbon. And so we get a partial positive on the carbon side and a partial negative on the oxygen side. And if you put a bunch of those molecules together, and pull them down, they'll kind of lock into those positions. Otherwise, they'll get into this position, and then they'll just suddenly a little bit of extra energy, and they pop away from each other. Another reason you can think of dipole-dipole forces being stronger is that it's in addition to dispersion forces. They still have electrons. They can still have those fluctuations in electron position, but now they also have this permanent magnetic force on top of that. If we compare between a polar molecule and a nonpolar molecule of similar size, so here we're looking at formaldehyde and ethane, their molar mass is about as close as you could possibly hope to get them without being identical. And the boiling point and the melting point are drastically different. So by adding in, is that 70? Yeah, it is about 70. By adding in that dipole-dipole force, we've gone from a negative 88 degrees Celsius boiling point to almost minus 20, a little past minus 20 boiling point. So that's a 70 degree Celsius difference. That's about the difference between like a warm day and boiling water. So that's pretty huge. And again, there's no like difference in dispersion force really, because they're about the same mass. So that's just a difference because of having the dipole-dipole force. And you can compare among things that have different strength of dipole-dipole force or different dipole force. So this chart that we're looking at, we've got dipole moment, so the strength of the dipole in a molecule, and we've got the boiling point on the y-axis. So higher boiling point, we would also expect to have a higher dipole moment. And these all have fairly similar molar masses, 44, 41, 46. So as we increase the dipole moment up to acetonitrile, we also increase our boiling point. Polarity, I feel like we've talked about it, but it's important for determining whether two things will mix together, which we call miscibility. You can sort of think of miscibility as mixability, whether the two things will mix together. I'm sure that's overlooking a crucial key detail, but that'll get you most of the way there at least. The phrase that we use in chemistry is like dissolves like. So things that are polar dissolve things that are polar, like dissolves like. Things that are nonpolar dissolve things that are nonpolar. This is important. This idea is important if you're working with a new chemical in a lab and you're like, what can I put this into? You could go look up the solubility of it in different solvents, because there's like a million solvents you can choose from, and figure out, okay, which one has the highest number, it'll go into that one best. But you might not have that solvent, and so you'll have to just pick something that's kind of similar in properties. So it might have great solubility in N-hexane. So, okay, well, we've got heptane, put it in heptane and see if that works. Or we've got xylenes, we can maybe try putting it in xylenes. Which of these molecules have dipole-dipole forces, if any? Another way you can read this is which molecules are polar? I guess I would include the have if we're replacing it. Instead of which molecules are polar. Is carbon tetraiodide polar? How many bonds does carbon like to form? Any ideas? It is 4. It's got 4 iodines on it. It's not going to have any lone pairs because it's carbon. It's small. It can't have an expanded octet. So carbon tetraiodide is a carbon in the middle with pop, 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 the 4 iodines attached to it. That'll have tetrahedral geometry. It's not particularly important here. The important part is no lone pairs and all bonds equal. Those are the 2 conditions for the nonpolar express, our fast track method of figuring out if something's polar or not, or rather if it's nonpolar. It meets all of those, and so this one is not going to have dipole-dipole forces. Our next one, we've got a similar idea. We also have no lone pairs. We're going to have carbon as our central atom. But our bonds are not all equal. So B, CH3Cl, will have dipole-dipole forces. And HCl is linear and has a polar bond. So it's polar. So C will also have dipole-dipole forces. Questions about any of those? All right, an electrostatic potential map, a heat map for the charge for acetonitrile, which is polar, is shown here. From this map, determine the geometry of how 2 acetonitrile molecules would interact with each other. Which of the orientations shown to the right is most likely? That's the wrong symbol. So the way that these electrostatic potential maps work is we've got a gradient from red on the right to blue on the left. The red is going to be our partial negative. The blue is going to be more partial positive, and like neutral being somewhere in between. And maybe also important, that doesn't track well. Those are the atoms that we have there. It's a little hard to see on the projector in class. So if red's partial negative, blue's partial positive, how will these little mini magnets line up? Did you say A? Yeah, it's A. Why is it A? Yeah, these line up. our little, they always look like music notes, I feel like, when I draw them. So our partial negative side is going to be attracted to the partial positive side. And so they'll line up in the same orientation. In B, they're not going to line up in this orientation because we'd be putting the negatives kind of next to each other. We might get some overlap from the pi bonding. I don't think that's likely, though. And D is the worst of these because we'd be putting the negative sides next to each other, and same polarity magnet sides don't go well together. Questions about dipole-dipole forces or about this image? I don't anticipate doing any heat mapping on anything. It might show up on the final, but probably not. Okay, hydrogen bonding. We will often think of this as a super dipole-dipole force. That means it's stronger. So this is a stronger dipole-dipole force, more selective than just being polar. We have our baseline being that we have to have polar molecules, but they contain one of these three bonds. Hydrogen bonded to fluorine, hydrogen bonded to oxygen and something else probably, and hydrogen bonded to nitrogen, and then probably two other things, R and R prime. The other things aren't particularly important. The reason that this is a stronger dipole-dipole force, if we look at the periodic table, or if we just think in our heads, what's the most electronegative atom or element? Fluorine. Way up there. That laser pointer's not working today. Way up there. And next in line, heir to the throne, oxygen, also very small. And next in line, after oxygen, nitrogen. So these are our three most electronegative elements. And crucially, they are also small. So our three strongest elements for electronegativity. And small. Small because they're in our n equals 2 row. They don't have access to as big of orbitals. If you go down to like chlorine, for example, now we're in our row 3. Chlorine is going to have an extra set of layers of electrons on top of what fluorine, oxygen, and nitrogen have. So it's going to be bigger. So we're going to get some partial charges. They're relatively large because of the big difference in electronegativity. That's the wrong button. What am I doing? Okay. We got most of it. Okay, and the other part is that they are in close proximity. So in our Coulomb's law, we had a bunch of stuff I'm just going to lump into a constant. We had Q1 and Q2. Those are our charges. Here we have relatively large charges. And on the bottom, we had radius or distance between the charges. So our Q1 and our Q2 are big. That's our change in electronegativity or our difference in electronegativity. And our R is small. That's the close proximity. And so we've got a recipe for a large charge. So hydrogen, that's the stuff you can drink. The oxygen and the hydrogen, because they're bonded directly to each other. And sort of on the end of the molecule, we get this strong partial negative and partial positive, and so the ethanol molecules will stack up. And we also have hydrogen bonding in water because we've just got hydrogen bonded to oxygen. So we get these strong hydrogen bonding moments between our water molecules. The hydrogen bond is the molecular force. It's not the force between the hydrogen and the oxygen or the fluorine or the neon, nitrogen. Compared to covalent bonds, these are about 2 to 5% the strength of a covalent bond, so they're way, 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 way weaker. But for intermolecular forces, they're relatively strong. This would be like me saying my cousin, my little cousin who's like 5 years old is really strong. Like, they're really strong, but for the context, which is they're 5 years old. Right? They're not like going to go up against Brian Shaw at a like world's strongest man competition. They would lose. It would be humiliating for Brian Shaw. I mean, for the 5-year-old, right? They're weak, really, but in the context of intermolecular forces, what we've got is strong. These hydrogen bonds are strong. Comparing two similar things, ethanol and dimethyl ether, which I think is what we were looking at before. So dimethyl ether and ethanol have the same chemical formula. Ethanol can hydrogen bond. And dimethyl ether is only polar. Actually, this might not have been what we were looking at. Doesn't matter. It's close enough. So if we look at molar mass, they're the same formula. They have the exact same molar mass. We're not looking at a difference of dispersion forces, just comparing hydrogen forces to polar only forces. And our boiling point for dimethyl ether is minus 22 degrees Celsius. And our boiling point for ethanol, which can hydrogen bond, is like 108, 106 degrees higher, if my mental math is mathing. So just by adding hydrogen force, our boiling point has changed by the difference between freezing water and boiling water, which I would consider a large difference. Water also notably has hydrogen bonding, like we saw, and relative to similarly sized and similarly classed molecules, it's got an extraordinarily high boiling point, which is great. So we're looking at a chart of molar mass on the x-axis, so sort of thinking about molar mass being a proxy for dispersion forces. As molar mass increases, dispersion forces increase. And we would also expect our boiling point to increase based on that. And our group 6A here, we've got H2O, H2S, so we're swapping out the oxygen for sulfur, then moving down one on the periodic table, selenium and tellurium. And also for group 4A, just to give us a comparison of what it looks like for other things, methane, SiH4, and so on, moving down. And we can see from our group 4A, right, as we increase molar mass, we also increase our boiling point. For our group 6A, where we have water, water is a weird outlier. This is way higher than we might expect if we didn't know about hydrogen bonding. If this trend held true, water would be, somewhere down here, well below 0 degrees Celsius, and so we probably wouldn't be dependent on water for life, because it would be all gas. If you had to choose one of these two to have a higher boiling point, just as a guess, HF or HCl, which do you think it would be? Yeah, it's HF. HF has hydrogen bonding. HCl is polar but can't hydrogen bond. And so HF has a higher boiling point being our proxy for stronger intermolecular forces. Questions about hydrogen bonding? Hopefully all relatively easy stuff. We also have, in the spirit of dipole-dipole force, ion dipole force. So this force, as you might be able to guess from the title, force between a dipole and an ion. This is our fourth and I believe final intermolecular force. This occurs when an ionic compound like salt is mixed with a polar compound like water. And that's what we're looking at in this chart on the right. So when we dissolve sodium chloride or salt in water, the water molecules all line up their partial positive or partial negative sides to the ions and latch onto them very strongly in the case of sodium and chlorine. And as everything is like moving around, they end up ripping apart the sodium and the chlorides. And that's how it dissolves. And then they exist in solution like this with a whole crowd of water molecules around them. Usually the thing that comes to mind for me is Buzz Lightyear in the claw machine pit at Pizza Planet with all the little green men around him, which I would show you, but it'll break the whatever I'm doing here. So this is our strongest of our four intermolecular forces. And that's kind of all we have to say about that. Taking a look at the four types of intermolecular forces again, we've got our weakest, our babyest force, dispersion forces. Everything that has electrons, molecules, and atoms has dispersion forces. And the strength we also have here on the right. So a little comparison. Very low number of kilojoules per mole to overcome those intermolecular forces. Our dipole-dipole forces, those are the ones that occur between all polar molecules because they've got partial positive and partial negative. And so they'll line up and stay in that formation unless you give them enough energy to leave. And those are 20 plus kilojoules per mole. And then hydrogen bonding, which occurs between anything that's got those three specific bonds, HF, HO, HN, is even stronger. And then our ion dipole force is much, much stronger than any of those. So some good things to know. The four types, where they're present or what causes them, and general trends. And comparisons. like the example problems that we did. I'm going to abbreviate intermolecular forces as IMF, not to be confused with the International Monetary Fund. Okay. Given what we know now, which of these substances has the highest boiling point? Even without knowing intermolecular forces, you might just be able to guess this one if you know the chemicals. It is A. To solve this type of problem, identify the intermolecular forces. Pick the one with the strongest or the most. In this case, they're the same. So the intermolecular forces that we have available, N2, being that it's just nitrogen bonded to nitrogen, is going to have dispersion forces only. CO is also going to have dispersion, because everything has dispersion forces. It's also probably going to have dipole-dipole. And methanol has dispersion, dipole, and hydrogen bonding. Because of that OH group, the alcohol group that's on it. And since it has the strongest intermolecular forces, it's also going to have the highest boiling point. Hydrogen bonding also exists in DNA. This is what keeps your DNA together. It might be nice to know that hydrogen bonding exists in DNA. You don't need to know how the base pairs work or what their letters are. But we've got a couple of base pairs. We get hydrogen that form these hydrogen bonds. In the case of our AT base pairs, we have 2 linkages. For C and G, we get 3. And those hydrogen bonds keep our DNA in these nice double strands until such time as they need to be replicated. I believe this is also where benzene, which I think we looked at the end of last class, it's like a flat disk with a delocalized pi bond system. I believe this is where that comes in. So it can slip its way in between some of these base pairs, and then that throws off the replication of DNA without it completely untangling. Okay, some other places that intermolecular forces come into play are surface tension, viscosity, and capillary action. The first one, surface tension, is the tendency of a liquid to minimize its surface area. You can quantify this amount. It's not very large. Basically, it's just how sticky the surface, or how, I don't know what I'm saying, but it has to do with the surface of the liquid. So water has really high surface tension, and so you can float things like this trout fly on the surface of water. You can also do, like in this previous slide, this is something you could try at home. You can put a little, that's not a toothpick, paper clip. You can put a paper clip, if you lower it gently enough onto the surface of water, it'll just sit there. There's also those like little water skater bugs that like move around on the surface of the water, and that's because of the surface tension. If you get rid of the surface tension with like a little bit of soap, those little skater bugs like flip underwater. They get back up over time, but that was something we like to do at summer camp. The reason for surface tension is because of intermolecular forces. So here we've got an example of the liquid, and we're going to assume that it continues out to the side and down. So up at the top, we're looking at the surface. Our molecules on the interior, in this example in 2 dimensions, this interior molecule can interact with 6 neighbors, and so it's kind of getting pulled every which way, whereas our molecules that are up on the surface aren't being pulled up, they're just being pulled down and to the side, and so it kind of pulls the surface inward a little bit. That's not how you spell molecules. All right, surface molecules are pulled in. And because of that, it's sort of, in my mind, it's like a little bit of a hardening of that outer layer. It also means that if you get like a spill or whatever, it'll also try to pull in as much as it can, and that's why we get water drops, like in these pictures. So the upper one, somebody on the International Space Station with a water drop out in space. You can get really big water drops because there's not gravity as much, at least, and also these water drops that form on this spider web. If you try to do this on the International Space Station with gasoline, for example, which has really weak intermolecular forces, it would probably just go everywhere, and then you'd be in trouble. Another thing that's affected by intermolecular forces is viscosity. The thickness of a liquid is one way that my brain thinks of it. Also, the resistance of a liquid to flow. High viscosity equals low or slow flow. And it's got a very fun unit called poise. We're probably never going to use it, but it's a fun name. Our viscosity is higher, greater, in things that have stronger intermolecular forces because they're stickier with their neighbors. So it's harder for them to move past each other. It also depends on the molecular shape. So we're looking at the viscosity in this table of several hydrocarbons at the same temperature. A bunch of N hydrocarbons, we looked at this in a different graph before. So pentane up to nonane, that's 5 to 9 carbons. And they're straight chain, so it's just add a carbon and 2 hydrogens. And the viscosity higher centipoise, that's our unit there, higher centipoise or higher viscosity along with the larger hydrocarbons. So we're seeing, we would expect, stronger dispersion forces as we increase our chain length for our hydrocarbons, and correspondingly higher viscosity. a classically viscous fluid is maple syrup. Motor oil has a viscosity that is high at low temperature. This is generally true for liquids, that viscosity depends on temperature. So motor oil in particular, it's convenient to have low viscosity at low temperature, but as you start running your engine, the temperature increases in your engine block, and the viscosity of, that's water at temperatures, the viscosity decreases as you increase temperature. As temperature increases, so does energy. Molecules can move past each other more easily. If you've ever tried to pour honey, honey also has very high viscosity, especially when it's cold. You might be like, well, the honey's stuck in the bottle. I'm going to break my hands trying to squeeze it out. So what do? You either heat up some water and you put the honey in it, or you throw your honey in the microwave for a couple seconds, warm it up, and then it runs a lot easier. You're decreasing the viscosity of your honey or your maple syrup or what have you. One thing that I think is fun that's sort of related to this is you can hear the difference between pouring cold water and pouring hot water, and you probably intuitively know how to tell the difference. I don't have cold and hot water to pour for you to demonstrate that, but I'm sure that you could find a video of that online. I've done it a couple of times. It's always spooky because you're just like, oh yeah, that's hot water, and it's not something you practiced. Anyway, that's fun. Sorry, there's whatever fluid that is, probably blood. Capillary thing. So capillary is the ability of a liquid to flow up against gravity in a narrow tube, a capillary tube, as they're often called. And we've got a combination of two forces. The attractive force between the molecules in the liquid, that's the cohesive force. We've got the co-prefix, prefix, and adhesive, like tape or glue. That's between two things. Two different things. So we've got the interaction between everything that's inside the tube and how much that likes its things. And then also the liquid that's inside the capillary reacting with the capillary tube and how much it likes, how strong that interaction is. If you have strong adhesive forces, then the liquid will tend to rise up the tube for magical reasons. This is part of how water climbs in trees, allegedly. There's some other things going on with that. So you can see this is a water-based liquid. If we have a wide capillary tube, it doesn't rise very much. As the capillary tube gets smaller, the water level rises more. The meniscus, that shape, that curve of the water, is concave because the adhesive forces are stronger. It will climb. So water notoriously will climb in small tubes. Mercury has a convex meniscus because its attractive force to itself, its its cohesive forces are stronger. So I would not expect mercury to climb in a capillary tube. Questions about any of these applications? Okay, I am satisfied with that for today. So we'll finish up hopefully on Wednesday.